In this lecture, we will start with by giving some more examples of continuous random variable. So we will start with what is called the exponential distribution. So this is basically nothing but, well, if you have this function, you can easily again check that this is a cumulative distribution function. And in this case, if you take small f to be this function, it is clear that if you take the integration of this function up to the point x, it will turns out to be this capital F. So this random variable is a continuous random variable having this PDF, and this random variable and these distributions are called the exponential random variables and exponential distributions. Note that if I change lambda, the distribution the cumulative distribution function as well as the probability density function changes. So this lambda is the parameter, and in this case we are going to use the notation x follows exponential lambda. Okay. Here I have given some plot of the density function and cumulative distribution function for different values of lambda, just for understanding how the shape of the cumulative distribution function and probability density function behaves for different values of lambda. Okay, so note that basically this is a bounded function. There is no question about that. This f is a bounded function and it is a decreasing function. And fx is also bounded because it always lies between capital Fx is always bounded because it also lies between 0 and 1. And these shapes are like this. That means that when I increase lambda, the distribution function shifts towards left. Distribution function shifts towards left, and it when lambda is big, we reach the probability, we reach the 1, the distribution function reach 1 more quickly compared to the smaller values of lambda. So this is just to have an idea how these functions look, how this distribution function and the cumulative distribution function and probability density function looks. Next example is normal distribution. It is a very useful distribution. Most of you have already heard of the name of this normal distribution. It is also called a Gaussian distribution. Both of them name are popular. So first point is that this function gives a cumulative distribution function. I left this is the exercise. Check that this function gives a cumulative distribution function by just you can use theorem 2.2 to check that this function is a cumulative distribution function. Now, once this function is a cumulative distribution function, it is very easy to see because this is written in terms of the integration. In terms of the integration, it is very easy to see that x is a continuous random variable having this PDF. And in this case, the distribution of a continuous random variable having this PDF is called a normal distribution with parameter mu and sigma square. Note that if I change mu or if I change the value of sigma, the PDF changes. So these two are parameters. So this is called with parameter mu and sigma square, and we denote it by x follows n mu sigma square. Note that this condition I need mu is greater than 0, otherwise this will not be a PDF because I will have a if sigma is negative, this whole quantity will be negative. There is a typo, this dx will not be there. There is a typo, this dx will not be there. I will make this correct in the class. So now if sigma is negative, that means basically this quantity will be negative, that this function will be negative, and that shows that it will not be a cumulative, it will not be a PDF because by definition PDF is a positive, non-negative function. So that's why this sigma greater than 0, these conditions we need to keep here. Well, if mu is 0 and sigma is 1, then the corresponding distribution is given a special name. It is called a standard normal distribution, and the corresponding random variable is called a standard normal random variable. Let us see some of the plots of cumulative distribution function as well as probability density function. So what I have done is that two cases I have taken mu to be 0, but I changed the value of sigma square. So the blue and green, if you see, that the mu, when mu is 0, their blue and green, these two functions here are centered at the point 0. So this is symmetric, both the functions are symmetric at the point 0, but what happens when I increase sigma, the function become more flat. So the thickness reduces and flatness increases. On the other hand, if you compare between blue and red, if you compare between blue and red, the sigma is fixed, but mu changes. So when you keep the sigma fixed and change mu, the function actually shifts, but the shape of the function remains same. The peak remains same, the kind of a spread remains same, but it's just a shift of the previous function. The red function is a shift of the blue function. So that means if I change mu, the location of the density function changes. Whereas if I keep mu fixed but change sigma, the spread of the function changes. That's why this mu is called the location parameter and sigma is called scale parameter. Okay. So again, these graphs are for understanding how these shapes look like. Next thing is basically two important theorems. The first theorem concerning the property of PDF. Just to recall, just to have a match, recall this one, that for the PMF, the two properties are that PMF is greater than equals to 0 for all x, and if I take the summation over the support, then the sum is 1. So in this case, the properties are almost similar. Note that that non-negative thing is there. This comes from the definition of the PDF directly, or definition of the continuous random variable directly. And the next condition, say condition 2, in case of the discrete, I have a summation, now I have an integration. Note that in case of the PMF, I have a summation of the support, but in this case, I have the integration over the whole real line. Okay, so two properties of the PDF are as follows. The PDF is greater than equals to 0 at all real values, and if I take the integration of the PDF, it turns out to be 1. And to see this one, it is very, very simple, because first one comes directly from the definition of the continuous random variable and PDF, and the second one, basically this integration is nothing but the integration limit a tends to infinity from minus infinity to a, and this is the now, because x is a continuous random variable, this integration is nothing but the distribution function at the point a. Now I take a tends to infinity, that means this quantity, this limit is equals to 1, using the property of the cumulative distribution function. The next theorem is thus the kind of a converse of this. If a function satisfies both the condition of the previous theorem, then it is basically a PDF. So if g is a function from R to R, such that g is greater than equals to 0 for all x belongs to R, and integration of g is equals to 1, then this g function is a PDF of some continuous random variable. Again, the proof we cannot give in this course, but yeah, this is a very important theorem in the sense that given a function, we can check if this is a PDF or not. And that is exactly we are going to do in the next two examples. So next example is a gamma distribution. It is again a very important distribution. In many fields, it is used like reliability field, like load sharing field. This is a very, very important. Also in case of server data, counter data, this distribution is very, very important. Okay, so how this distribution arises? This distribution arises something like this. Notice I am not going into the proof. Proof is given in appendix 2.a. You can see this one, but the fact I am telling you that, well, if you see this integration is an improper integral. The reason is basically nothing but this infinity is included here. And this improper integral converges if alpha is strictly greater than 0. If this alpha is strictly greater than 0, then this improper integral converges. And this improper integral diverges if this alpha is less than or equals to 0. Okay? And this statement gives rise to a distribution function of a continuous random variable. How? Okay, let us denote this one as this thing converges. So let us use a, obviously the exact value of this is not possible to compute for general value of alpha greater than 0. Let us, but it converges, so let us denote it by a notation which is this gamma alpha. Note that if I change alpha, the value of this integration will change, so I write it as a gamma alpha. It depends on alpha. Now, now if I divide this quantity by this one and take the integration, so if I take this quantity in this side, so what will happen? It will happen that integration 0 to infinity 1 by gamma alpha e to the power alpha minus 1 e to the power minus t is actually equals to 1. So what I mean to say is that, well, if I take this, I have that gamma alpha is equals to 0 to infinity e to the power alpha minus 1 e to the power t dt, which basically tells that integration 0 to infinity 1 by gamma alpha e to the power alpha minus 1 e to the power minus t dt equals to 1. Moreover, this function is always greater than equals to 0. Okay, this function was always, in fact, strictly greater than 0 on the positive part of the real line. So that means basically if I take a function fx which is exactly 1 by gamma alpha e to the power alpha minus 1 e to the power minus t, if t is positive and 0 otherwise, then if I take the integration, if I take the integration of this function, if I take the integration of this function, the integration from minus infinity to 0, then integration from minus infinity to infinity, f of x dx equals to 1 because of this, because the negative part of the real line integration is 0, only the positive part will going to contribute, and that integration is 1. So the integration is this function is 1 and this function is greater than equals to 0. That means this small f function is a probability density function, so of some continuous random variable, and this is used, and we can define a probability density function like this. Only thing change we have made is that this beta has been incorporated here. If beta is there, I have to also take beta to the power alpha here, and it is very easy to show that this integration of this function is 1 and this function is greater than equals to 0 just by using what we have discussed. Okay, so that means that this is a PDF. That means that this is a PDF, and a random variable having this PDF is called a gamma random variable, and corresponding distribution is called a gamma distribution. Note that again, if I change alpha or beta, the PDF changes. So this alpha and beta are parameters, and we will use that x follows gamma alpha beta here for noting or for denoting this particular thing, that x is a continuous random variable having PDF this. Okay, some graphs are given in figure 2.3. You just check, it is given for different values of alpha and betas, and you please check this one. I am not going into the graph. Next one is beta distribution. Again, it is on the similar flavor, that this integration, this is an improper integral. It will be improper integral if alpha is less than 1 and near x equals to 0, we have a problem. If beta is less than 1, we have problem near x equals to 1. Okay, and if both of them are less than 1, we have problem near 0, near 1, and if both of them are greater than equals to 1, we have no problem. This is a proper integral. Okay, fine. And the point is that if alpha is strictly greater than 0 and beta is strictly greater than 0, then this integral converges. And that gives rise to a distribution, because now I will denote this integration as beta alpha beta. This is capital beta, not b, beta alpha beta, and we can define a density function by dividing this one, and so a random variable having this density function is called a beta random variable, and the corresponding distribution is called beta distribution. Note that again I have alpha and beta are the parameters here, because if I change alpha and beta, the density function changes. So we have all these density functions. And one point I should mention here, note that if you take alpha equals to 1, then this x term will not be there. Similarly, if I take beta equals to 1, this x term will not be there. And so this gives the uniform random variable. Okay, so alpha equals to 1, beta equals to 1. If I take alpha equals to 1 and beta equals to 1, beta alpha beta distribution coincides with uniform 0 1 distribution. Okay, you have some work here to do. You have to check why the gamma integral, this what is called the gamma integral converges for alpha less than equals to alpha greater than 1, and that is given in appendix 2 point A. Similarly, the why this integral converges, that is given in 2 point B. You need to check these two, and also in 2 point B and 2 point A, some information regarding the gamma and beta the integral are given. Please go through them because they will be useful throughout the course. Okay, so next one is basically one example, and we'll stop then. So this example shows that there are random variables which is not discrete, not continuous. So what we have done, the random variable, we have seen two categories. Category 1 is basically discrete random variable, category 2 is basically continuous random variable. Now natural question is that is all the random variable can be divided into only these two categories? And this example shows that no, it is not. There could be some random variables, there are some random variables which are not discrete nor continuous. Okay, which are neither discrete nor continuous. So what is the example? Example is basically given in terms of the distribution function f, where we had the distribution function look like this. So let us just draw this distribution function. Let us just draw the distribution function and let us check how it look like. So in this case, the distribution function, so this is the example 2.20. So the distribution function given to us is 0, x plus 1, 1 if x is less than minus 1, if minus 1 is less than x, is less than, here I have equality, less than minus half, and 1 if x is greater than or equals to minus half. Okay, so in this case it is very easy to see that the distribution function actually looks like this is the point 0 0. So I have minus 1 here, I have minus half here. So the function is 0 throughout this. Then at the point x, the function value is 0. So the function now increases like this. At the point half, if I take the left limit, it is nothing but plus half. So this value is plus half. Then I have a jump. And the function continues. Here it is open. Okay. So the distribution function is continuous throughout R except the point minus half. Now, if I want to check whether the random variable x is a discrete random variable or not, what I have to do? I have to start with the set D, which is the point of discontinuity of the distribution function, which is minus half in this case. And then I try to find out what is the probability that x belongs to D, which is nothing but in this case, what is the probability x equals to minus half. And this probability is nothing but what is the length of this jump here, which is nothing but half. So clearly this quantity is not equals to 1, and that this shows that the random variable x is not discrete. Okay. Now is this continuous? No, it is not continuous, because we have already pointed out if x is a continuous random variable, the cumulative distribution function has to be a continuous function. But in this case, we have seen that this distribution function is not a continuous function. So that means the corresponding random variable is neither discrete nor continuous. But note that in this case there is an interesting point here. Note that this distribution function, which is neither discrete nor continuous, can be written as this form, where this f1 and f2 are two distribution functions, and f1 is a continuous distribution function, is a distribution function of a continuous random variable, and x2 is a distribution function of a discrete random variable. And that breakup can be done for any distribution which is not a discrete, not a continuous. Any distribution function which is not a distribution function of a discrete random variable, nor a distribution function of a continuous random variable, can be written as a convex combination of two distribution functions. One of them is a distribution function of some continuous random variable, another of them is a distribution function of some discrete random variables. Okay, I hope this thing is clear. I stop here, and we'll see new concept in the next lecture, which is expectation of random variables.